So let's move on to the application of the projection. So given some data points, say coordinates for instance, how to get the best possible line through them. So I have 4 data points like 1, 1, 2, 2, 3, 2, 4, 5. Those are the coordinates, x and y coordinates. And if I plot them in Excel actually and find a trend line, I actually get a trend line, and it will actually show me the equation to the trend line y is equal to 1.2 x minus 0.5, and the r square, the coefficient of determination, is 0.8. All these things actually come from linear algebra, come from whatever we did so far. So that's what we want to kind of understand. Now, clearly these points are not consistent as a system of linear equations. So that's what I want to show you first. If I were to take just the first 2 points, 1 and 2, so I would get that line. If I were to take points 2 and 3, I would get that line. If I were to take 3 and 4, I would get that line. None of those 3 lines is actually a good fit. So throwing away anything other than 2 points is always a bad idea, because there is information, and you can see that the best possible line is actually the blue dotted line, blue dashed line rather, and all the red dotted lines are bad lines. So we have to get to the dashed line. So how would we do this? So I have data points, and what I'm saying is that there is a model mx plus c is equal to y. So I just put in different values for x and y in mx plus c equal to y. So I get 1, 2, 3, 4 equations. If I have that, I have 4 equations and 2 unknowns, m and c, 2 unknowns. So let's find out if there are solutions. So I want to write it in the form of ax equal to b. So A, my matrix, is 1, 2, 3, 4. That is the coefficient of the first unknown, m. So 1, 2, 3, 4. And the second unknown is c, 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 c. So the coefficient is 1. So 1, 2, 3, 4 and 1, 1, 1, 1. That is my matrix A for this system of linear equations. 4 equations, 2 unknowns, m and c. And now my unknowns are m and c, and my constants vector is 1, 2, 2, 5. Now I'm writing ax equal to b, and there is no solution for this one because the equations are not consistent. If you actually do the Gauss-Jordan elimination, you will see that the third row will have something that implies 0 equal to non-zero. Now I can go and do my recipe. I'll take A transpose A, and A transpose A inverse. So I'll do all that. A transpose A inverse A transpose. So a lot of arithmetic calculations to be done. After doing all that, your reward is that you get x hat, which is the best possible estimation of m and c, m hat and c hat. That will be equal to x A transpose A inverse A transpose B, and I get this. And if you look at it, it is 6 by 5, that is 1.2, and minus half, which is minus 0.5, which is what you had, which is what Excel told you. So that's what you will get. So what Excel is implementing is not an iterative way of getting at the solution. It's actually a closed form computation. Given some data points as coordinates, how to get the best possible line through them, what you will do is get m hat and c hat, the variables in the system of linear equations, m and c, those are the variables, and you have to find the best values for those, and that will give you an equation, and that equation is the best possible line. And even the coefficient of determination is given by the error vector, the green E vector, because that shows you how far away you are, the difference between the projection and the original constants vector, but that gives you an indication of how good your fit is. That was the first example. The second example, I want to go back to, I think this was week 5 or 6 or something, where we had 3 equations that did not have a solution because they went through 3 different points. There was no common point in the coordinate space. X plus y equal to 5, x minus y equal to 1, and 3x minus y is equal to 9. 3 different lines, no common points. And at that point, I asked you what the best possible solution would be. We kind of guessed that it could be the centroid maybe. But now we are much more sophisticated in terms of our linear algebra ability. So we can actually write ax equal to b, 1, 1, 1 minus 1, 3 minus 1, that is a. My x vector is x and y, and b is 5, 1, 9. And then I can take A transpose A transpose A inverse, and then that. Then I can get the best possible value of x and y. I get 3.5 and 1.83. That is the best possible value, and that is actually inside this triangle. 3.5, that is here, and 1.83 is actually somewhere here. That doesn't look like the centroid, but it is somewhere inside the triangle. And if you just compute the centroid, which is just the mean of all the x values and mean of all the y values, that gives you 2.17. That looks more like here. So there is a difference between actually doing it the linear algebra way and then our intuition. Look at the centroid. The reason why the centroid doesn't look like the right one is because we are not actually working in this space. We are working in a different space. We are working in the vector space. And there is one more reason. That reason is something I would like you to discover on your own. And if you cannot discover in 1 or 2 weeks, maybe ask me in the last lesson, and then I'll tell you what it is or what I think it is. I will invite you to figure out why the best possible solution is not the intuitive centroid but something else. And this has some implications on the K-means algorithm, which actually uses the centroid, and how it compares with linear regression, etc. So it's got implications in machine learning. So that's why I would like you to think about it. Let's take a real data set to understand this better. So the whole data set is basically a matrix. So I have a data set here. This is a real data set that I collected from my students a couple of years ago to do some project. So I asked them for their height, their weight, and their length of hair estimated, and their age, and their sex, male or female. So as you know, males tend to be a little older than females in Singapore because of the national service, and they tend to be a little taller and heavier, and they tend to have shorter hair. And we can probably create a statistical model out of it, which will be a linear regression model. So each column is a column of a feature, height or weight or length of hair or something. It's called a feature. And each row is an observation. So there are 5 features here and many observations, 127 really. So it is a very tall matrix. You have to be a bit careful because in some situation, people think of features as rows and observations as columns, though not very common. And so you have to be careful about which way it is really. So let's look at the data. So I have 127 numbers. If I were to plot them, I have 5 different variables really. I think I'm going to ignore age. I'm showing height along the x-axis, weight along the y-axis. So people who are taller, they tend to be heavier. So there's some kind of line here. And then I'm showing the length of hair by the size of the point. So you can imagine that there is an axis coming towards you from the plane, and that is small numbers farther from you and bigger numbers closer to you. So bigger numbers look bigger because they're closer to you. So bigger bubbles for people with longer hair. So you can kind of see that these blue points are probably girls. They tend to be smaller and lighter, and the orange points are probably guys. So this is a visualization, and we're trying to build a model for this. So it's not just one variable versus one variable, but we have more than that. So let me look at it once more. What I want to do is to take height and length of hair as independent variables, things that I can measure. I want to take weight as the output variable, something that I want to predict. So I have some data here. I have the red ones that are inputs and the green ones that are output. So that is my training data. And I want to implement an intercept that I'm going to add 1. Remember, for mx plus c, for c we had 1s everywhere. That column of 1s will happen here also. So I have an intercept implemented by 1. So I'll start with ax equal to b. My A matrix will be all my red numbers here. B will be my independent numbers. And x is my parameterization. X really is my model. So A is that. Regression parameters, typically people use the symbol beta for it. So it's a vector, beta vector. That is a model. So the 3 numbers there will specify the model for you. And my B vector is the output. That is the what we call the dependent variable y, the thing that depends on the input. So this is what we have. And to use the right nomenclature and right symbols in the world of linear regression, people usually write ax equal to b as x beta equal to y. And the solution then will be x beta equal to y will not have a solution, but multiply by x transpose on both sides, you will have a solution that will give you the best possible estimation of the parameters beta. So that's the game that we're going to play. So x is called the design matrix, beta is the the model, the statistical model, those are called the regression parameters. There will be n of the plus 1 because I added the intercept. And in most programs, most statistical programs, you will have the freedom of saying that the intercept is 0. So there's a no intercept model also, in which case the regression parameters will have only n parameters coming out of the model of the program. Then the target variable will be the training data set. You will have as many as the number of observations. Now, in order to get the statistical model, the regression model, all you have to do is to just do this multiplication. You have x, so take the x transpose. You have x transpose x, the gram matrix, as a small matrix, takes its inverse, multiply, and y is all known in the training data, and that gives you a set of regression parameters coming out of the data. That is a training process. As you can see, it's not iterative. It's a straightforward matrix multiplication. We have very good algorithms to do this, and it is determined. It's a very beautiful algorithm to actually get to the regression parameters. Okay, so that's what I wanted to show you. So x beta equal to y. X is the design matrix, and that is the measured independent variables. Beta is the model regression parameters. Y is the measured dependent variables in the training data set. And based on the training data set, what's the best possible beta that gives you, and that is given by x beta is equal to y, multiply both sides by x transpose, and put a hat on beta, and that's it. That is the best possible beta that you can get. So now you might ask, why are we doing this? Why do you want to get this model? What's the purpose of getting the parameters beta? Because once you have the model, you can predict a new weight. If a new person comes in, I don't have a weighing scale, but I only have ways of measuring the height and the length of hair. Once I have the model, I can actually predict what the weight is going to be. And this is basically the basis of predictive analytics using linear regression. It's a supervised machine learning algorithm because we have labeled training data. So the way of doing it in linear algebra is elegant, geometric, thinking about the projection. Calculus will give the same answer, of course, but it's tedious and messy. So the squares, actually the fact that it's the least square minimization, the square actually comes from the fact that is we are using Euclidean